So I'll start with an apology to First Hour. If they watch this, this will probably go much better than it did for them, because it's the second time. All right. So today, and I didn't make like the objective paper because once again, I didn't have any time this morning. We're talking about calorimetry. Yes, but at all. We do constant pressure, which makes the math unbelievably easier. All right, so since we cannot know the exact enthalpy of the reactants and products, we measure the change in enthalpy through, which is defined as the measurement of heat flow. Okay, so there's your definition of calorimetry. This is a really important concept. Do you remember the very first day I showed you 3 questions? Yeah, this is on 2/3 of those 3. No, it's not the whole question. So it's more like 1.5, because it's half of one question and all of another question. So calorimetry is very important for your future grades, and it's not really that bad. I did confuse a lot of people first hour. No, I'm not bagging on them. I'm bagging on me in this instance. Like, it's all on me. So you guys have the benefit that the wrong things I say, I've already been called on, and I get to fix them and not say them to you. It's a huge advantage to you guys. All right, moving on. Now, to understand calorimetry, we first have to talk about heat capacity and specific heat. So the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius is its heat capacity. All right? We define specific heat capacity, or simply specific heat, which is what we really care about, as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. All right. Does anyone recognize this number? All right, that's what 1 calorie equals, right? But it also was the energy required to raise 1 gram of water, 1 degree Kelvin or Celsius. We can say Celsius or Kelvin because, remember, the difference between a Celsius and a Kelvin is the same. All right? Meaning like the same amount of energy for 1 to 1. No. 1 degree Celsius and 1 degree Kelvin are the same thing. And Caitlin, this is for you, Chini. The other one in front of you. Now, 1 degree Celsius is not the same temperature as 1 Kelvin. Just if I go from 2 to 3 Celsius, it's the same change as 2 to 3 Kelvin. Yeah. No, not individually. Because remember, Kelvin is just Celsius plus 273. So there's no like division or subtraction or anything. So they are the same gradations is the big nerdy word. Yeah. Right. All right. So I probably overcomplicated that. But this is a number we really need to know because we're going to use it in our calorimetry because we're going to do these things in water. All right. Now, specific heat capacity, specific heat or the specific heat capacity, whatever, is defined as the heat transferred divided by the mass times the temperature. So if you're ever asked to find specific heat, S is equal to Q over M times delta T. Now, you can write the one at the bottom. That one's the one you'll use 1,000 times more than the top one. Yes, Reyes. What's that? Right. That's true. Sometimes specific heat is called C. All right, CS or just S. They mean the same thing. On the video, I think, didn't he use both? I can't remember. But Either one is fine. C or S is fine. You will see the S on the AP test, so I would just use that. Okay. Now this equation can be written differently to solve for Q. And Q is what we really want because Q and delta H are pretty much the same thing, correct? So the equation that we will use way more often is actually that Q equals SM delta T. Now, just to chop that up, we will do this in water. So S is 4.184. M is the mass of your solution. Be careful, your solution means your solute plus your solvent. It doesn't mean just one or the other, it means them combined. And then the change in temperature. We okay with this so far? Okay. Yes, solution. All right. Now, by carrying out a reaction in aqueous solution in a simple calorimeter, such as the one to the left, one can indirectly measure the heat change for the system by measuring the heat change for the water in the calorimeter. Please recall that the heat the system loses is absorbed by the surroundings and vice versa, correct? So I can measure one or the other and they will be the same, just whether it was gained or lost would be different. Are you all right with that? Okay. Typically, the book, I sure can. When the system loses energy, it will be absorbed by the surroundings, or vice versa. The surroundings might lose energy and the system absorbs it. Now, it's an equal exchange, so I can measure the change in the surroundings and it will tell me the change in the system. Because it's pretty impossible for me to measure the actual energy given off when something dissolves. I don't have any probe that will look at the solid and measure the heat and all that by when it's given off. But I can easily measure the change in the temperature of the water, and I know they have to be equal due to the first law of thermodynamics. Okay, so that's what we're going to do. We're going to insulate this so that there's no heat loss to the environment, so that the reaction or dissolution is the thing giving off heat or taking it in, and then it just changes the temperature of the water, which we can measure very simply. So that, when I said you had to draw a picture, this is your picture on your test. You need some sort of coffee cup, or if that offends you, a hot chocolate cup. Okay? You need a thermometer, something to stir, and then usually we just throw a cork on the top. That's literally all you have to draw to get 5 points on that question on the test. Yep, it's pretty simple. All right. This is called constant pressure calorimetry because there's nothing to increase the pressure here. And yes, there's a cork stopper on the top, but there's at least 2 holes in it, right? This thing will vent and it will maintain room pressure at the entire time the reaction's happening. All right, I already said this, but because the specific heat for water is well known, which is 4.184 joules per mole Kelvin, we can measure delta H for the reaction with this equation. Q equals ms delta T, as written here. Heat is equal to the mass of the solution times the times the specific heat times the change in temperature. Well, S is. I wrote this. S is. I usually have it SM delta T. I don't know why I wrote it that way. We don't have a mole Kelvin. We're just multiplying. It's joules per mole, but then we're measuring it in the change of Kelvin. So it's not moles of Kelvin. It's just the way the units work out. If that makes sense. Okay. So, time for some practice problems. All right, you can see the answer right there. Let me erase all this. But here we go. I add 30 grams of sulfuric acid to 200 milliliters of water, and the temperature goes from 25 to 45. And then the rest of the problem is just asking you, what is the heat released, or what is the enthalpy change? You want to do it together? All right. So Q is equal to SM delta T. So what is S? 4.184, and that is a number you definitely should memorize. All right. The mass is the mass of the solution, which is both the solute and the solvent. Now please recall that the mass of water and the volume of water are related in that 1 gram is equal to 1 milliliter. That's its density. So this is really 200 grams of water, correct? So this number is what? 230. And then the change in temperature was my final minus initial. It's just 20. All right, now I end up with what value? I erased it. It's a big number. It's like 19,173. Is that right? Oh, wow. 19,246.4. Thank you. I apologize to you and your whole family and grandparents. All right. Now, that's joules, correct? Typically, delta H is asked for kilojoules because these are huge numbers. So we would really say this is 19.25 kilojoules. Are you okay with that conversion? Okay. Now, I neglected to tell first hour something. Do you think that this process is endo or exothermic? Okay, you know it's exo from what? Because the water got hotter. The water's the surroundings. So this is an exothermic process. So when I wrote this out, this technically Q is equal to negative SM delta T. The reason we throw that negative in there is to make the final minus initial math work out. Now, you don't actually really have to know that anyway, as long as if you know it got hotter, that your math better be a negative number. If you know it got colder, your math better be a positive number. So I don't even put the negatives in, I personally, until the end. I just look, hey, did it get hotter or colder? All right. So 19.25 kilojoules. Are we okay with that? You want one more? All right. So I don't really like writing them all out. So if you have NaOH, and we'll say we're going to put in 35 grams. We're going to say our water is 300 milliliters. Now let's say, I'll just give you delta T. The change in temperature, let's say it went up 13 point. Actually, I'm going to change that. It's going to go up 11.13, which is important. Why? Because that's my birthday. When are you guys ever going to figure this out? All right. I'm going to have a party. I'm hopefully timing it so the test is on my birthday. It is cool. Thank you. Okay, will you try this problem on your own? I will. 4.184. I know, that was a good one. No one's ever going to watch it. Anyway, 335, correct? Okay, by the way, this is usually the most missed thing you forget to add them. Because remember, the density of water is for every 1 milliliter, it's 1 gram per milliliter. So really, it's just a 1-to-1 ratio. So this is 300 milliliters, but it is also 300 grams. You okay with that? Okay, the change in temperature is my birthday, which is 11.13. All right, 0.1975. Not really, but it would be. Okay, what did we end up with here? Uh-oh, that was too many. So 156 something 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 joules. All right, we're going to put it in kilojoules. Raise your hands if you're okay with this. I'm such a better teacher now. All right. Teacher. All right. Would this be endothermic or exothermic? Exo. Good call, Liam. Yes. It's the specific heat of water. It's how much energy is required to raise 1 gram of water, 1 degree Celsius. Okay. I'm going to explain this negative one more time. If the temperature of the surroundings goes up, it has to be an exothermic process. Exo, because if the surroundings have more energy, that means the system has less, right? And that means it lost it, so it has a negative sign. So if the temperature goes up, you do need to put a negative in front right there. What's that? You can think it through, or technically Q is equal to negative SM delta T. I just keep... Yeah. Correct. Yes. Most of us have negative feelings towards our eggs. Thank you. All right. So far, so okay? All right. Now, I don't know why, besides that I sucked at teaching it at first, but the next part seemed to just blow their minds. So, it won't, Olivia, I can almost guarantee. This was negative 15.6 kilojoules were released when 35 grams dissolved. Are we okay with what that really is? This much was released when that much dissolved. All right, this on a test, this will be asked to you. That will be A. And you would put negative 15.6 kilojoules. B would ask you to do the following. And just don't panic yet or at all. Just give harder. And don't just look yesterday we had a little delta H value and we same number as A. You thought it would be? Okay, well, you're a very good thinker, so look here. 35 grams of NaOH. Is that 1 mole? It's not, right? Okay, so B says delta H in kilojoules per mole. So to solve that piece of the puzzle, you need to find out how many moles you have. So how many grams of NaOH did I give you? 35 grams NaOH. It's 40, what? It's just 40, isn't it? All right, I'm going to round it to 40 grams per 1 mole. So 35 40ths was around 0.6 something, I think. Someone divide 35 by 40. Oh, 0.875. Sorry, I'm an idiot. No. Be careful. This is how many moles, right? What is this asking you for? Okay. Okay, so please look. All you do is take your kilojoules now, negative 15.6 kilojoules, and it wants it per mole, so you just put it per 0.875, and then you have the unit of kilojoules per mole, so that you know that's what you want, and you just put the answer right here. It's negative what? Are we okay with that? Okay. So to just slowly talk it through one more time, this whole process, you first use your specific heat equation to solve for delta H, which is Q. Now, hey, remember Q and delta H are not exactly the same thing, but mathematically and in this class, for all intents and purposes, they are the same thing. So it's kind of annoying that the equation doesn't just say that delta H equals negative SM delta T, because it sort of doesn't, but it really does. I know, chemistry's weird. But anyway, we use this equation to find the kilojoules. That's the kilojoules per the given mass. The next step then would be to convert the mass you were given to moles by dividing by the molar mass. Then, once you have kilojoules, and once you have moles, you simply divide the two. Okay. One more? Yeah, I'm just going to write this one out. So let's say that KCl dissociates whatever, and let's say I have, 20 grams. Let's say that my mass of water, or my volume, was 300 milliliters. Which Griesbach really means what? 300 grams. Good. All right. And let's this time say my change in temperature, it went down 10 degrees. This time it will be a positive. Okay. Now, I would like you to solve for, first off, A, the Q of this process, and then B, the delta H in kilojoules per mole. So, I'm sorry. Some of you read 20, but whatever. Here we go. If you did 320, you got what number? All right. If you did 70, what did you get? 16.4? Oh. Okay. All right. I will take either answer. I'm not even going to look at these. You know we did the process right. So, all right. We have that part. So that would be A, correct? Now, B requires us to now convert these. And this will be a pain. If you do 20 over 74.5, you get something. If you do 70 over 74.5, you get something different. Who did 20? What'd you get, Caitlin Post? 0.268. Who did 70, Olivia? 0.94 something. All right, both of these were moles, correct? All right, so if you did 20, you would now take 13.38 and divide it by that. If you did 70, you would now take 15.4 something kilojoules and divide it by that. And so if you did the 20, what was your answer here? 0.7374? I'm just going to go dead center. If you did 70, what did you get here? What's that? All right. I will mentally accept either answer because my handwriting. How many were able to successfully do that? Raise your hands. Okay. Mentally dead. I'm sorry. Become a donor. All right? Your organs are still useful. All right, now, the next thing we're going to do is the problem I was working on when you guys were discussing things with Brienne. So, I do have to discuss the positive or negative things here, right, Reyes? Okay, so please look, and everyone, please pay attention to this piece. Tom Davidson is lazy, but Tom Davidson's somewhat smart and has done this a long time. So he knows, hey, if the temperature goes down, what sign is my answer going to have? It's going to have a positive. So I do the signs at the end, and it's mostly because of when it is endothermic. This number here was technically a negative 10, right? All right? But if I put a negative 10 in, I get a negative 10 or negative answer. But remember, this whole thing here is really negative of this, so it gets a positive, right? But I've screwed up my whole life with double negatives or 1/2 negative, 1/2 positive, whatever. So to me, I just do it at the end. But yes, Caitlin, the 10 should have been a negative because it did go down 10. But then you do need to remember this whole answer is times a negative. Does that make sense? Okay. All right. The next thing we're going to do is we're going to solve for grams now. What is that? N-E-E-D-E-D, whatever. That says needed. That says L-I-O-H. You know what? I bought this for this exact reason. All right. Here we go. Because sometimes my handwriting isn't very good. Right? We can do this together. Oh crap, this is complicated. Here. I used to think she was a pretty nice kid. But not anymore. Oh, jeez. Oh, gosh. You ever get a new keyboard and it's slightly off of your old keyboard? That's my... Okay, fine.
David, you got to make that text about 3 times bigger. I'm pretty sure people still can't read it.
Are you... You are kidding me. He's joking. We'll just go Kelvin. Now, you need to know something, by the way. Because you need... Actually, I should have just... Hold on. That's a... I'm going to put it right here, actually. It's because it really belongs here. Okay, just let me fix one thing, and then we're going to be good. I feel like this keyboard was probably a waste of my time so far. CL, right? Okay. Now, the question, this would be part C to this question. Where am I? Part C would come from part B, which came from part A. It says, how many grams of KCl are needed to heat 300 grams of water, 1.8 degrees Kelvin? Now, I'm going to use this value from now on. I'm not going to do the double math. Are we okay with that? All right. Now, just look. What does this value ultimately means? It means this. KCl, solid, dissolves to K plus Cl minus, and then our delta H was equal to what? This value, 49.7. So this would be cool, right? Because I said this went down. Sorry. All right. So this number that we found in B is that number that goes there. Okay. So now let's work through this together. How many grams are needed to cool 300 grams of water? Oh, I screwed up a ton. Solution. 1.8 degrees Kelvin. That needs to be solution, or the math is quite a bit harder. But you won't. You'll just do solution. You're going to be fine. Okay. So it's going to end up being another problem where it's just calorimetry combined with enthalpy. So calorimetry, we know the equation is that Q equals SM delta T. Are we okay with that? All right. Now, we have some of these values. We have S is 4.184, correct? Yes. Yeah. Okay. All right, it's 4.184. What's the mass of my solution? 300. Now, I don't know what part of that is KCl. That's what I'm finding, but I don't care. I know the total of the solution is 300. Now, what's my change in temperature? 1.8. So I'm going to solve this problem. Please do that math for me. Oh, I wonder if... Oh, that won't work. It's 2259. Uh-oh, go away. So 2.26 kilojoules. Everyone okay with that? All right. Okay, now, this is kilojoules that are required. Hold on, I got to think. 2.26 kilojoules. But what am I trying to solve for? Grams. So I'm going to do a little picket fence here. What do I need to get rid of? Kilojoules. Do I have a kilojoule anywhere else? It's right here, right? You with me? It's this piece right here. 49.7 kilojoules. But what is that per? That's per 1 mole. And then how do I get rid of moles? 1 mole. And we're back to 74.5, right? What do I get? 3.37. Okay. Sorry, I had to remind myself because it's just a picket fence. I won't tell you what I thought wrong because then you're like, oh, well, why wouldn't I think that way? Anyway, sort of tricky, but is it doable? Okay. You want another one? Okay. So remember, by the way, this is all a series of problems. It will come from an initial experiment that you get data from. And then you use that data to come up with the kilojoules for the reaction, and then you can do a lot of stuff from there. All right. So let's say how much time? Oh, we have like 2 minutes. I'll give you one. We'll go over it tomorrow. Ready? So let's just do LIF because that's easy math. Let's say it's 25 grams. My water, we'll just say it's 100 milliliters. We'll say that the temperature change went up 7 degrees. So A, you're going to tell me what Q is. B, you're going to the H in 7 degrees. 7. Olivia, are we good there? No, nothing. I just want to make sure this is a 7 degrees, not 70. All right. And then C, I want to know how many grams to heat 500 milliliters, 20 degrees Celsius. When you get that answer and it's a huge number, that's fine. That should be a much larger number than the one we just did. 2 grams to heat. Okay, you guys are awesome. Thank you.